Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. So recently I woke up having a whole bunch of batteries about which I knew very little, if anything. I had no idea if they are still full, completely empty, or somewhere in between. Now, of course, there are ways to test a battery, especially if you're like me and if electronics is your hobby, then you surely have some devices in your mini lab to test batteries. However, using multimeters and an artificial load to test batteries every time can be a bit of a hassle, and we generally want to have a more elegant solution, preferably a device into which we can place the battery and we can test the battery a lot more easily and without too much stress and too much work. There are all sorts of battery testers out there on the market. However, I generally don't like them, and the main reason I don't like them is because they test a battery and they attempt to determine a battery's life by simply measuring the voltage while the battery is in the air, how we say it. The battery is not connected to anything else, it's left open. And this doesn't give us good results, because there are times when a battery still has a decent voltage when absolutely nothing is connected to her. However, once we connect something to her, a consumer that starts to draw current from her, well, then the voltage drops dramatically. So the proper way to test a battery is actually to apply a load and then measure the voltage and determine how much, based on how much the voltage drops relative to the nominal voltage, if the battery is still good enough or not. Just the open circuit voltage is not good enough. So, because I wanted to do something like this elegantly and simply and just directly, I decided to design my own battery tester and to build him, and there he is on the screen right now in front of you. I am yet to 3D print a plastic cover on top of the circuit and batteries, the batteries with which the circuit is powered. This is why you still see pretty much everything opened to the public, so to speak. But other than that, the tester is 100% finished. So this is what I want to present to you in this video. This is what I want to show you how to do. The schematic might look a bit scary, but trust me, it is actually relatively simple, and I will guide you step by step through it. The idea is that I wanted a battery tester that can test at least 3 kinds of batteries, or perhaps 4. 1.5 volt AA or AAA batteries, 9 volt batteries, as well as the so-called coin cells. We call them tablet batteries, like the ones that are used in all sorts of smaller devices like clocks and stuff like that. I wanted to be able to test those as well. Some of those batteries have 1.5 volts, some others are lithium 3 volt batteries. I wanted to be able to test them, so I needed to have a certain level of flexibility. Therefore, I opted to have a large array of currents that I needed to draw from the battery in order to load the battery, and then display the voltage across 8 LEDs. Why 8? Because each LED has to be driven by a comparator, and we can have up to 4 op-amps in an integrated circuit to be able to work with. So if we use 2 integrated circuits that have 4 op-amps inside, then we have 8 op-amps to work with, so we can have 8 different levels that we can detect and display through 8 different LEDs. So this is what I'm going to be explaining starting this is what I'm going to be explaining in this video. When it comes to circuits like these that tend to be more complex, manufacturing them at home can become more difficult. Luckily, there is PCBWay, a leading PCB manufacturer with many more capabilities to help you build even your most difficult projects. You can easily get an instant quote for PCB manufacturing from the website's front page, upload the Gerber files, and have your PCBs created in just 24 hours. Need more to get your project finished? They also offer PCB assembly services with manufacturer direct pricing, so you can have your PCBs delivered with components soldered on. This way you don't have to do the tedious work yourself. Or perhaps you want just the schematic stencils, so you can solder the components yourself. Just finish your design in your favorite design software, upload all the necessary files to PCBWay, and you'll be contacted by one of their professional representatives after they manually review your project, offering you a one-on-one customer service to make sure that your circuits get fabricated just the way you want. Are you building a circuit for a device that will need a case in the end? Then they can certainly help you with that as well, offering you 3D printing or injection molding services to have your custom-made plastic case, or perhaps CNC machining services to help you with a custom metal case. All you need to do is go to PCBWay.com. The link is in the description. Thank you PCBWay for sponsoring this video, and now let's get started with the circuit. Alright, so like I said, the idea was to be able to test as many kinds of batteries as possible. By the way, when I say batteries, I really mean batteries, not accumulators, okay? So in English you say rechargeable batteries, and by extension you call batteries pretty much everything. Not in my language. In my language we call whatever you call rechargeable batteries, we call accumulator, okay? So that we make a clear distinction between batteries that can be charged and batteries that cannot be charged. So when I say batteries, I strictly mean batteries that cannot be charged. Those are the ones that we want to be able to test, because chargeable batteries, they don't make sense to be tested. You can just plug them into a charger and charge them back to 100% or whatever other voltage you want to have. So you know, testing them doesn't make that much sense, at least not in this particular way, okay? So this tester is just for batteries that cannot be recharged, okay? So I wanted to be able to test 9-volt batteries, 1.5 volt batteries, as well as the so-called coin cells like these. You know, Chere 2032, 2025, AGE 13, stuff like that. Some of these have 3 volts, like these lithium ones, okay? Some others have 1.5 volts. So, like I said, the main idea is to draw a current from them. Now, in order to draw a current from a battery, all you need to do is just simply place a resistor in parallel with the battery, and that's it. The problem is, if you want to be able to test multiple kinds of batteries, then placing a resistor is not enough, because based on the voltage of the battery, you will get higher current or lower current. And that considering that we want to have a range from 1.5 volt to 9 volts, which is 6 times bigger than 1.5, placing a single value resistor will automatically give us a current that spans also from 1 current to the 6 times that current. So that would ended up being a problem. So because I wanted to have the same current no matter what kind of battery and no matter what kind of voltage that battery has, I was basically forced to create a constant current source that I would apply to the battery. And this is what we see in the beginning. Okay, we see a couple of transistors. Ignore the fact that there are 2 of them. I will explain in a moment why. For the moment, consider just one of them. Okay, we have a couple of diodes that are basically turned on by a R3 resistor, which gets to be powered from the batteries that power the entire circuit, which are 3 1.5 volt batteries, 4.5 volt in total. Okay, and these transistors are also connected to a couple of resistors and together to the testing battery. You have a collector resistor which has a maximum value of around 6 or 7 ohms. We cannot have a higher value here because we want to be able to test 1.5 batteries with 100 milliamps of current. And based on the collector emitter saturation voltage of the transistor and whatever voltage we have on R7, which I'll explain in a moment, then we don't get left with much voltage for R2. So this is why R2 has this small value. And we have R7 here, which is connected by default, but in parallel, which we can optionally connect another resistor of another value based on what push button we push. The idea is that this resistor and, well, the equivalent resistance that is found here, it can be just R7 resistor or R7 in parallel with any one of these. If we press one of these buttons, will essentially dictate the constant current that this circuit will draw from the testing battery. The idea is that if we have here a constant voltage across both of these diodes, and we can also consider that we have a constant base emitter voltage on the transistors in order to turn them on, then we will not be able to have a variable voltage here on this resistor. We will also have a constant voltage across this resistance, which is going to be exactly the difference between the voltage on the diodes and the voltage on the base emitter of the transistors. If this voltage would ever try to increase, then the base emitter voltage would decrease, which would turn off the transistors, which in turn would limit the current through R7. And vice versa. If through R7 we would have a too small current, then the base emitter voltage would increase and these transistors would turn on harder, which in turn means that they would pass a larger current through R7, which would make the voltage across R7 increase back. So anyway, the idea is that these voltages will essentially remain constant during the whole functioning of this constant current source. And because they remain constant, a constant voltage across a constant resistor also implies that we will have a constant current here through this resistor. But this resistor is in the path of the current that's been drawn with this constant current source from the battery. And this is how this constant current works. This is why we will, regardless of the voltage of the battery, we will always have a constant current, simply because there is this equilibrium formed here between these voltages, and this is why it's impossible for the current to rise above this threshold that is dictated by the voltage here divided by the resistance here. Of course, the current can drop below that threshold when we simply don't have enough voltages in our circuit to keep this running. But the current, again, the current cannot surpass that particular threshold, and this is what is important. Now, I wanted to have an entire range of currents, and I wanted them to be available to me at just a click of a button. So I used a bunch of push buttons. I will show you towards the end of this video. We will go to the workbench and I will demonstrate how this device actually works. So I have a whole bunch of push buttons, each with one resistor, or in some cases two resistors in series, because I needed to have a non-standard resistance. And these are placed in parallel with this R7, so we are essentially modifying this equivalent resistance here, and by extension the current that we are drawing with this constant current. And I wanted to have a wide range of values. The absolute smallest value that we can have should be around 100 microamps. If we take a look at these very low power batteries, okay, like these 2032 lithium batteries, they have around 200 milliamps hour of capacity. And if you take a look at the typical drain of this battery, it is rated 190 microamps, you know, and it tells us, okay, we have about 1200 hours of functioning or something like that. So it was clear that, well, even if we wouldn't have been told this, it is clear that the smaller the battery is, the smaller the capacity is, and therefore, by extension, the smaller the maximum current that we can draw from it can be. And these small batteries are made to work with hundreds of microamps, maybe milliamps at best, but at currents of milliamps, they drain pretty fast. So I wanted to start at 100 microamps and move forward towards 100 milliamps, because 1.5 volt AA or AAA 3A's batteries, they can draw, they can supply up to 100 milliamps or close. So the smaller batteries need to be tested with smaller currents, larger batteries need to be tested with larger currents. So by default, R7 here of 10 kilo ohms would make this constant current source draw about 100 microamps. If it does not have any other resistor connected in parallel, meaning if we don't push any of these buttons, then R7 alone will dictate a current of about 100 microamps, which is, in my opinion, the absolute smallest current that makes sense to test a battery with. And if we press one of these buttons, then the resistance will drop, the current will increase, and we will have these steps, which are approximate. I didn't bother to, you know, to actually have very, very precise currents here, because that's it doesn't make sense. We want to have approximate current. So approximately 250 micro, 500 micro, and then 1 to 5 milliamps, 10, 20, 40, 75, and 100 milliamps. A small mention is that the level of 100 milliamps is actually for 1.5 volts. If we press this button and we have a 9 volt battery that we want to test, actually the whole circuit will draw more towards 150 milliamps. But anyway, that's a bit besides the point. The point is to have this wide range of values. Okay, so this is how we change the current. Now let me get back a little bit to this constant current source, and before I move over to the rest of the circuit, explain why two transistors in parallel like this and why I used BC 639 instead of, I don't know, 547 or 2N2222 or something else like that. Well, the idea is that first of all, if I want to draw 100 milliamps from the battery, I need to be able to have I need to use a transistor that basically is capable of handling 100, at least 100 milliamps easily. For BC 547, 100 milliamps is the absolute maximum collector current. We obviously don't want to find ourselves at the absolute edge, so we need to use a transistor that can handle more than 100 milliamps as a maximum. The second reason was because these usual transistors have about 500 milliwatts of dissipated power. Well, at 100 milliamps here, for a 9-volt battery, we can have about 8 volts across the transistor alone, which means about 800 milliwatts of dissipated power, which would be too much for one of those usual low power transistor. So I needed to use something better, and something better, well, there's this family of transistors from BC 635 to 640. Some of them are NPN, others are PNP, but all of them basically can withstand 1 amp of collector current continuously, which is important, which is good. We will never get anywhere close to 1 amp, and 800 milliwatts of total device dissipation, okay, which is what we need. However, we would still find ourselves a bit at the edge with this dissipated power if we would only use one transistor. So I decided to just put 2 of these transistors in parallel so that I can split the current through them and therefore split the dissipated power. Normally you don't just place 2 transistors in parallel like this, but since it's still low power circuit, no matter how imbalanced these transistors would be, they would still take some of the other's current, and therefore we can be rest assured that no transistor will have the entire current passing through him and the entire dissipated power that he needs to withstand. So this way we make sure that no single transistor needs to withstand the full 800 milliwatts of dissipated power. Okay, this is why I put 2 transistors in parallel. And that's about it with the constant current source. Now let's move forward a little bit towards the end, and then I'll come back here towards the middle to explain what's up with these buttons, and I will show you in the end how I implemented them. Now we have a battery which is loaded by a constant current source. Now we can just take a look at the battery's voltage and display it somehow. For me, a bar graph of 8 LEDs was good enough. In order to do this, just have 2 integrated circuits with 4 op amps each, placed this way, connect all the plus inputs, also non-inverting inputs, connect them together, and then connect them to the battery. Theoretically, we could connect them directly to the battery, and then the minus inputs, the inverting inputs, connect them to different threshold voltages, so that each op amp will basically be a comparator, will compare that threshold voltage with the battery voltage, and will turn on the LED if the battery's voltage is higher than that threshold voltage. And this is what we have here, basically, nothing special. For a 1.5 volt battery, I have calculated well, I wanted to have LEDs turn on from 100 millivolts to 100 millivolts, so from 1.5 volt downwards, 1.4, 1.3, and so on up until 0.8. But we basically have a few problems to solve. First of all, what happens if we test a 3 volt or a 9 volt battery? Well, then we cannot simply connect the inverting inputs directly, the non-inverting inputs directly to the battery. We would have to have a voltage divider. Okay, for a 3 volt battery, we would have a voltage divider that basically halves the voltage, and for that we can just place two resistors in series of equal value and take the voltage from the middle, and that's it. We would have essentially dropped down the voltage from 3 volts to 1.5 volts. Of course, the thresholds for our LEDs will not be from 100 millivolts to 100 millivolts. They would be from 200 millivolts to 200 millivolts. So basically, we would have 3 volts, 2.8, 2.6, and so on up until 1.8 volts, 1.6 volts, sorry, the lowest LED. Similarly, we would need to do with 9 volt battery, but we would need to have a bigger attenuation. So if we place a 390 kilo ohm resistor in series with an 80 kilo ohm, then we would have a 1 to 6 ratio, and we would drop 9 volts to 1.5 volts and all the other voltages accordingly. So for that we would have steps from 600 millivolts to 600 millivolts. Okay, so the first LED would turn on at 9 volts or above, the second LED at 8.4, the third at 7.8, and so on until for 4.8 volts, the first LED from the bottom. Now, we want these voltage dividers to be as high as possible so as not to load the battery, because again, we want to be able to have around 100 microamps of current as a default current. So obviously we needed to place here some pretty large values for these attenuation resistors. So I chose 822 kilo ohms, just like that, just an arbitrary choice. And based on that, I calculated that 390 kilo ohm, which is another standardized value, is good enough for a 9 volt battery. And together they are a high enough resistance so that batteries will not be loaded by these resistors, which will basically be constantly connected to the battery when we are testing the battery. Okay. If you divide 1.5 volts to, let me show you, 1.5 volts to 82,000 ohms, which will be connected constantly to the battery, it results in 18 microamps of current, which is an order of magnitude smaller than the 100 that we have by default from the constant current source. So not a problem. Same with 9 volts divided by how much is it? 472,000. It's also around 18-19 microamps. So it's good enough. It doesn't interfere with the 100-ish microamps that the constant current is drawing by default. The second problem that we have is that we need to basically switch from these attenuation levels. So we need to have different switches, but ideally we should not need to, manually press these switches when we are operating them. Ideally they should sort of switch themselves automatically. And I managed to do that, but for that I will show you, I will need to go to the workbench, so I will show you then what was my solution to this problem. In the schematic they appear as simple switches. in reality they're not, well, they are simple switches, but the way they get triggered is what I would call an ingenious way. Anyway, so now we have a normalized voltage that we can test against, which is 1.5 volts regardless of the voltage of the battery. Now we could theoretically feed this to the totality of the non-inverting inputs of the op-amps. However, I didn't want to do this directly because I just did not knew what the input impedance of LM324 is, which is the integrated circuit that I chose to use as a quad op-amp. I'm pretty sure it's high, but it's something that's not stated in the datasheet for some odd reason. So the idea is that if we place 8 of these op-amps in parallel, basically whatever impedance is at the input, however high it is, it will get diminished by a factor of 8. And that might pose a problem. It might essentially screw around with R6 here with the 82 kilo ohms that I've put here, and basically drag down this voltage. So I decided to just to be on the safe side, I decided to place a buffer here. Okay, this is why you see this op-amp as a buffer. I decided to just place a buffer between this voltage divider and these inputs. And I chose LM358, which is electrically equivalent to LM324. It's just that this IC has only 2 op-amps inside. And because I had the other op-amp available, I decided to buffer the reference voltage as well. So in order for these op-amps to work as comparators and compare the battery voltage with something else, which needed to be these voltages from 1.5 volts downwards, okay, we need to generate those voltages. So I decided to use a Tele 431 that without any further resistors, it will give us 2.5 volts reference voltage. I am feeding it with about 2 milliamps of current from R1, 1 kilo ohm, and I'm buffering its voltage not because I have to, but because I just have a free op-amp that is within LM358, and I can do something with him. I have to do something with him. I cannot just leave him floating because it's not a good idea. So I decided to buffer this 2.5 volt reference voltage. And of course, this 2.5 volt reference voltage needs to be stepped down, and created several steps from this voltage in order for us to have from 1.5 to 0.8. And this is why we have this long list of series of resistances here, of resistors. A 10 kilo ohm first to bring the voltage down to 1.5 here in this point, and then a 1 kilo ohm resistors, several of them in series, with an 8.2 kilo ohm at the very end connected to the ground, so that in each intermediate point across and around these 1 kilo ohm resistors, we have 100 millivolts of difference voltage between the two pins. So we have these reference voltages here. And well, this is pretty much everything that it is to the circuit. It's nothing super complicated, it's nothing over the top, it's just the basic requirements, but they are done in a way that is actually useful and you know, can actually help us. I've chosen 4 red LEDs and 4 green LEDs, just for fun, just for you know, having a sort of differentiation to make it easier to see how many LEDs turn on and off. They don't necessarily represent something. Although if you think about it, for a 1.5 volt battery, if it drops down to 1.1, we can kind of consider her to be, well, consumed. For a 9 volt battery, if it drops down to 6.6, it's absolutely clear that it is consumed. For a 3 volt battery, on the other hand, these data sheets basically make the statement that they can drop down to 2 volts and they should still be considered okay. Below 2 volts, they should be considered to be consumed. So technically speaking, for a 3 volt battery, we should treat it as okay up until the last 2 LEDs. So anyway, this was just my choice. You can of course use multiple colored LEDs to make it even easier for you. Bear in mind that you will need different current limiting resistors for each LED, depending on the depending on the color that it has. It will have a higher or a lower voltage drop. So yeah, for the red LEDs I chose 180 ohms. For the green LEDs, 100 ohms, or even though I should have probably placed even smaller resistors, because the green LEDs don't shine so brightly. But anyway, they are still good enough. Now, this is pretty much everything that I wanted to talk about when it comes to the theory. It's not much to it. Like I said, the circuit is not complicated. It's just complex, because I have a whole bunch of buttons that trigger a different kind of current, and I wanted a wider range of currents. And since every LED requires 2 resistors and 1 op-amp, of course the whole circuit will tend to become bigger, but bigger is not necessarily more complex and more difficult to understand. So yeah, this is pretty much the schematic. Now let me go to the workbench and I will show you in real life how this device works. We will get to test some good batteries, some not so good batteries, and we will see how it performs. All right, so this is the tester, as I told you. So 3 batteries that power the circuit. This is the circuit. It's done with that with one of my not orthodox methods of creating a circuit, so to say it like that. I will put the link in the description. I've made a video a while ago about how you can make circuits with a board that has no copper whatsoever, and we will use the wires of the brand new components to create traces, because we don't really need more than that. I used rectangle shaped LEDs because I liked them better, and they typically look better as a VU-meter, as a bar graph. Here are the push buttons for the various currents that we want to draw, and I am still left to 3D print a cover, a plastic cover, and put it here. This is why you still see the whole circuit with the wires and everything. An on-off switch at the top that I will need to glue, and these are the placeholders for different batteries that we want to have. Those voltage divider for each batteries are placed externally. I have not placed them on the actual circuit. So this is why you see some resistors here, because we need to drop down the 9 volts to 1.5 volts. and from 3 volts again to 1.5 volts. Those 3 resistors that I mentioned earlier. Now, those 3 resistors came with a switch. Whenever we place a battery and we want to test that battery, we need to basically close that particular switch. Well, I did not want to do that manually, so I placed switches here in each placeholder, so that when we put a battery here, it would automatically press against the switch, you know, and it will turn on the switch. And if we manually press that switch on 1.5 volt batteries, then the first LED will turn on, which is normal. It's a sign that the circuit is working. But of course we will not do so unless we actually place a battery here. So let's get to work. Let me show you how this works. Okay, let me start by testing a CR2332 3-volt battery that's brand new. I opened it from the package earlier. To show you this, I have this multimeter here, and here 3.3 volts. As usual, brand new batteries have a higher voltage than the nominal one written on it. So normally when you place 1.5 volt AAA or 9 volt batteries, you don't have to manually press the buttons. However, for these very small batteries, when you place them in the placeholder, you have to gently press against, you know, the triggering button in order for the button to start working. This is the only case when you actually need to do a little bit of work to press on the button, but you can do so with the same hand that you're holding the battery. Okay, so as we can see, this 3-volt battery, we measured it earlier, 3.3 volts. It turns on all of these LEDs. Okay, and we can test it at various currents. So right now it's been tested at roughly 100 microamps. Press the first button, 250 microamps, second 500 microamps, and because it's a brand new 3-volt lithium battery, it can actually be tested with milliamps. So 1 milliamp, 2 milliamps, 5 milliamps. Of course, these kinds of batteries are not to be loaded with milliamps, but just for the sake of testing and showing you here, 10 milliamps I've pressed earlier, and now 20 milliamps, and at 20 milliamps we see that the first LED drops down, which is absolutely fine because this kind of battery should not be loaded with that high current. So this was a good battery. Now let me show you a battery that will basically not do anything at all because it's just 0.3 volts, right? So it's just beyond. And not only that it's 0.3 volts, but this is a 10 megohm multimeter, and 10 megohm is still too low resistance, and the voltage of the battery just cannot hold, and it keeps dropping. Needless to say, if I put it here and I press the button, nothing happens because 0.3 volts is way below the threshold here of 1.6 volts for the 3-volt batteries. So this is the kind of battery that can definitely be thrown to the garbage. 1.5 volt AA battery, okay, 2 A's. Brand new battery, good shape battery. Okay, I can show you if you want to see. 1.6 volts, right? We place it in the spot, click, and that's it. Like I said, the battery herself has pressed against the push button, so it has connected the wires appropriately. All LEDs turn on, of course. And since it's a brand new battery, we can start from the highest current and go down. Okay, so 100 milliamps. At 100 milliamps, come on, focus. At 100 milliamps, we don't have any LED turn off. Okay, the first time it turned off probably because it was I don't know, a small shock, but then I see that it stays on. Of course, since it's a brand new battery, it can actually provide 100 milliamps. So of course it doesn't make sense to test the battery with lower currents if we have no LED turning off at 100 milliamps, then it will not turn off at lower currents either. So this is clearly a good battery. Okay, let me show you triple A battery that's not good anymore. It's not 100% depleted, but it's got 1.19 volts. Okay, and needless to say, we could still use her for very low currents, but not for higher currents. And now I get to show you the benefits of such a device, of being able to essentially test the battery with varying degrees of current drawn from her. So we place the battery in its place, make it so that it makes contact. Only the four red LEDs turn on, the green LEDs remain turned off, because again we have below 1.2 volts, so 1.5, 1.4, 1.3, 1.2. We saw earlier that we have 1.19, so this is why only these are lit. And now let's start from 1 milliamp and go upwards. 1 milliamp okay, 2 milliamps okay, 5 milliamps okay-ish, 10 milliamps still okay, but probably if we would hold for longer it would not be okay. 20 milliamps still okay, but it would probably go down faster. 40 milliamps, we have one LED that turns off, so basically the voltage drops even below 1.1 volts to 1 or a little above 1 volts. 75 milliamps, same. 100 milliamps, it drops even below 1 volt. And probably if I would hold it longer, it will drop even before this as well. And now if I release, the voltage will slowly go up back, but this is a clear indication that this battery cannot be used in high current devices anymore. Okay. So I would not throw this battery immediately to the trash, but I would consider it partially consumed. Let's test the brand new 9-volt batteries. Need to be careful with the polarity here. Okay, one thing I need to mention about 9-volt batteries, they are not meant to give as high current as 1.5 volt batteries. So if we test them with 100 milliamps and we see that even though they're brand new, one LED gets turned off, it's absolutely normal. 9-volt batteries are not meant to supply high currents like 100 milliamps. They're meant to supply lower currents. They compensate by having a higher voltage. So basically the power is somewhat similar to 1.5 volt batteries, but because they have higher voltage, they can supply lower currents. They have a higher internal resistance. So 100 milliamps, as we see, drops in voltage. 75 milliamps, not a problem. The voltage still remains at that level. And of course, lower currents will also make it work the same. So the last battery that I will test, another 9-volt batteries that up until recently I had no idea if it's still good or not. So I placed it. Now I know because I've tested it earlier, but essentially this is not a depleted battery, but it's not quite as brand new as the previous one. Okay, so at 100 milliamps, 2 LEDs turn off. At 75, 1 gets turned off. At 40, again, 1 gets turned off. The previous battery was holding at 40. At 20 milliamps, we get to have the voltage, the full voltage. But it is possible that if I keep pressed longer periods of time, you know, the battery will go down. So the fact that at 40 milliamps I still get 1 LED turned off tells me that this battery is still good, but it's not at full capacity. It has been used for a while, and therefore I need to be careful with her. So that's pretty much it. This will, for me, this will definitely be a very, very useful device to test all sorts of batteries. Yeah, so I recommend that you build one for yourself if you are dealing with batteries a lot, and if you want to know what's their current state of health. I hope you found this useful and interesting. Thanks a lot for watching. I will be posting this schematic in Patreon for those who will be interested in building this. You can, of course, take the schematic from the screen and just, you know, redraw it yourself, or you can download it from the Patreon. Thanks a lot for watching. I will see you next time when we will see how to build something equally useful and interesting that will surely be a good tool for the future. So thanks a lot for watching, and I will see you next time. Bye bye.